Today we are going to talk about anti-disassembly techniques. First we will see how disassembler works, then we will see various techniques which makes static analysis a little bit hard. So let's start. Let's talk about disassemblers. These are the tools which converts binary to assembly code. Here we took an example of a hex representation of a binary. Here we can see the disassembler take opcode and operand and convert this to its corresponding assembly language or say assembly code. Here we can also see the instruction length is variable. For example, the call or E8 opcode takes only 4 bytes. So the total instruction with opcode and operand becomes 5 bytes. But on the other hand, move EAX EBX only takes 2 bytes, just 8, 9 and D8. So this is the variable length nature of binary instruction. This is just awesome. The disassembler uses two disassembly algorithms. First one is linear sweep and second one is recursive descent. So let's talk about each one by one. Let's talk about linear sweep algorithm, which is the simplest disassembly algorithm. Here the disassembler reads the binary from top to bottom and converts it to assembly sequentially one by one. For example, the disassembler will first look as first byte and consider it as opcode and takes the next number of bytes as operand, which the number of bytes depending on how much bytes the opcode demanding. Here move only need 1 byte. So the 8, 9, D8 becomes move EAX, EBX. Then the disassembler will go to next byte and read the opcode and takes as much operand the opcode needs. So here it will convert this whole instruction into call address instruction. Then it will go to next byte and it will sequentially go one by one byte and convert this to assembly code. But it has a major flaw, which is it consider every byte as instruction. So if a binary have any data part, the disassembler will also try to convert the data into instruction. For example, after return, the binary sample have a data part which is hello text, but the linear sweep algorithm will try to convert the first byte to an instruction code and take it as an opcode. So the 048, which is binary of H, it will be considered as decrement EX. So the whole control flow of the binary will be disrupted or destroyed. This is the major flaw why the recent modern disassembler don't use this algorithm. Instead, they use the recursive descent algorithm. So let's see. Let's talk about recursive descent algorithm. Modern disassemblers like IDAPRO, Ghidra use this disassembly algorithm. In this algorithm, the disassembler never goes outside the control flow of the program. It do this by doing just two words. First one, it stores the address of control flow instruction in queue and second one is stopping at the final instruction. For example, a final instruction is return. Let's see in this example. Here, first the disassembler will sequentially disassemble each instruction until it find in an control flow instruction. Upon finding a control flow instruction, it stores its address in a queue. Then first it will store the calls, this address, then it will then it will start decompiling. When it will find the jump 0, which is another control flow instruction, it stores its address in queue, and it will go on, and then you will find jump not 0 instruction, and it will stores its address in the queue, and it will go on until it find a final instruction, in this case which is return. And when it hits the final instruction, it goes to its queue and starts disassembling from this instruction. And in this path, when it will find any control flow instruction, it stores its address in the queue, and upon hitting the final instruction, it will come to the queue and starts from A2 address, and it will go on. By doing this, we can see it will never go outside the control flow of the program, and it will never reach this data part. So the data part will never compile to any instruction, and it will remain as binary. So the users will see the data part as binary, and this part will never become any instruction. This is the beauty of recursive design algorithm. Previously, we got a high level overview of how disassembler works. Now it's time for the main topic of this video, which is anti-disassembly techniques. In this video, I talk about 4 techniques, which is the most common as anti-disassembly technique you can find in binaries. So let's talk about one by one. Let's talk about first anti-disassembly technique, which is putting fake or say decoy opcode in the middle of instructions. For example, we put E8 as a fake opcode in the middle of these 2 instructions. So what will happen? First, the disassembler will convert 31C0 into XOR EAX, EAX, and then it will come to 74, which is a conditional jump instruction, and it will store its offset into its queue. And then the compiler will come to E8, and it will treat this E8 as a legit opcode and convert E8 to an call instruction and take the next 4 byte as operand. So this whole instruction become the call address instruction, and which is not true. Our true instruction is this one, but putting this fake opcode, the whole instruction become this. And after hitting the final instruction, when the compiler will come to this queue, it will see that the address is already disassembled, so it will not reassemble the whole instruction. So the whole instruction will remain this false instruction, and disassembler will start disassembling from this location. But in dynamically, when the XOR EAX, EAX instruction will be executed, the 0 flag will be set, and as 0 flag will be 1, the jump 0 address instruction will always execute it. So after this instruction, the program flow will jump to this address. In the middle, garbage or fake opcode will be completely ignored, as disassembler will treat this fake opcode as a legit opcode. It will convert the whole instruction set into a different instruction. Here we took jump 0 as our control flow instruction. We can put any other control flow of instruction here instead of jump 0. For example, we can use jump 0, jump not 0, any unconditional jump, and any other control flow instruction. Here we took another example, which is jump to an location, which is unconditional jump. So this jump will always be happen, and after this jump we put some garbage or say fake instructions. So what will happen after disassembling this instruction, the disassembler will come to this address and it will disassemble this instruction. So the whole alignment of the binary will be changed. This will result in two things. First, it will convert the whole binary into different assembly code, or it will just show some invalid opcode. Although this code will not do this trick in recursive descent algorithm, because in recursive descent algorithm the unconditional jump instruction is treated as a final instruction. So the whole disassembler will start disassembling from this instruction. But in linear sweep, because this doesn't happen, in linear sweep, after converting this instruction into an assembly instruction, the disassembler will come to this address and convert this instruction into assembly, and then the whole alignment of this binary will be changed. So that's how we can trick both recursive descent and linear sweep algorithm by putting a fake opcode in the middle of the instruction. Let's see second anti-disassembly technique, which is called EIP manipulation. In this technique, after a call instruction, we put some junk byte, and we design the call function in this way that dynamically the whole junk instruction will be ignored and the execution will go to the valid instruction. Here, after this call instruction, we put some junk byte, and the disassembler will try to convert this junk byte into a legit assembly code. So this leads to a different assembly code or some error in the disassembly view. Here this function pops EAX, and after this pop instruction, EAX will have this address, this instruction's address, and then we add EAX with 03. So EAX will now having this instruction's address, and then we will directly jump to this instruction. So dynamically, after executing this instruction, the program flow will directly jump to this legit instruction. But as the disassembler try to convert this junk byte into legit assembly code, the whole disassembly view will be wrong, or the whole disassembly view will be full of error or invalid assembly code. The next technique is return pointer abuse. Generally, any function ends with RET or return address. The working of the return address is it just pops the address present in the top of the stack and jumps to that address. But in this technique, before return address, we push some hidden payload's address. So now the top of the stack is having our hidden payload address, and the return address will pop the top of the address which is in the top of the stack, and which is the hidden payload address, and it will jump to the hidden payload. But the disassembler doesn't know this, so it will disassemble the instruction after the call instruction. But in reality, we will never go to the next instruction after call. We will just go to a different address, which is the hidden payload. Now the last anti-disassembly technique is FS0 modification. This is one of my favorite technique. In this technique, we first raise a divide by zero exception, and then we change the value of FS register. By changing the value of FS register, we can change the execution flow of the program to any address we want. First, let's see how Windows handles exception in 32-bit binary. First, the exception occurs. In this example, it is divide by zero exception, and then hardware interrupt occurs. Then the CPU goes to kernel mode. In kernel mode, the CPU stores the state of the current thread with the exception record and create a structure named exception record structure. Then the CPU comes to the user mode to identify and resolve the exception. The FS register stores the exception list of current thread, and in user mode, the KI user exception dispatcher function will be executed, and this function reads the address of the FS register. And after reading the address of the FS register, or we can say the address of the exception list, or say the exception handler list, the handler pointer is extracted. Then the exception record structure is passed to the handler function, and then the handler function identifies and resolves the exception. And then if the program handles the exception by try except method or any other exception handling method, if the execution of the program resumes, and if not, the program crashes. Windows only use this process to handle the exception in 32-bit binary, because this process has a major flaw. That's why this process doesn't apply in 64-bit binary. Windows handles the exception in 64-bit binary differently. The flaw here is if we change the value of FS register, we can change the program flow to anywhere we want. In this process, we misuse this flaw. First, we push the hidden payload address, the address where we want to go. The stack pointer is pointing to this address. Then we push the value of FS0 register, and the stack pointer is pointing to this address. Now we put the value of stack pointer to FS0 register. Now the FS register is pointing to this address, and then we raise the divide by zero exception by these two instructions. And now as we changed the value of FS0 register, the exception handler function is now our payload. And by this technique, we can jump the execution flow to the payload. As the disassembler doesn't know about any of this, it will just disassemble the instruction after DVX. But in reality, the program flow will never come to this decoy instruction. It will just go to the hidden payload. Now this is a fantastic technique which makes the static analysis a little bit harder. Alright, that covers the 4 techniques for today. Before we wrap up, I want to clarify something. My goal with this video wasn't to give you an exhaustive list of every single disassembly trick out there. There are a ton of them. The real goal here was to show you the mindset. I wanted to demonstrate exactly how and why malware authors intentionally manipulate their binaries to break our tools and make static analysis a nightmare. It's all about understanding that a disassembler is just software making assumptions, and authors can weaponize those assumptions against us. If you found this video helpful, let me know in the comments, and maybe we can cover more advanced obfuscation in the future. Thanks for watching, and I will catch you in the next one.